Professor Sourav Chatterjee is a professor of mathematics and statistics at Stanford University, USA. The Infosys Prize 2020 in Mathematics was awarded to Professor Sourav Chatterjee for his groundbreaking work in probability and statistical physics. He is recognized in particular for his contributions to areas such as fluctuations in random structures, concentration and superconcentration inequalities, and first passage percolation. Professor Chatterjee is one of the most versatile probabilists of his generation and is known for his formidable problem solving powers. We welcome you, sir.
Okay, thanks for the invitation. I've never spoken at a school before, actually. So, I've given talks in other places. So this is a new experience for me. So the last time I was in front of a school audience was when I was in class 7, and they asked me to participate in a debate, and it's kind of somebody opted out, and so they asked me, and I was not good at that. So I stood in front of the whole audience. I couldn't speak. I just couldn't speak because so I was nervous. So that was my last experience speaking in front of school. So this is a second time. Okay. So I hope that will not be repeated. Okay, so let me share the screen right away to avoid any kind of mishaps later on. Let's see. So I practiced this already, so it should be okay. Okay, so I'm going to write things, and so let me keep this here. I was told that there'll be students from class 6 to class 12, all kinds of students here, and all ages, and so it's very hard to prepare a talk that'll be accessible to everybody, and at the same time interesting to everybody. So let's see if I can tell you some interesting things. Um, so what do mathematicians do? That's one thing. I hear some music. Is that part of the program or no?
No, 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 no.
Okay. Okay. So mathematicians, professional mathematicians, solve problems. So the students here, let me talk to the students that. You solve, you take a problem, and sometimes it's difficult, and you spend some time trying to solve it for your class, and that's the kind of problem solving. Now, what professional mathematicians do is that they solve problems which have not been solved before, so people haven't been able to solve those, and then they solve it. And then there are various kinds, various levels of those problems. So some problems you may have heard of, like there are these famous problems from number theory that some of you have certainly heard about, the twin prime conjecture or the Goldbach conjecture. But those have been open for hundreds of years, and that's a different thing. But then there are all kinds. There are thousands and thousands of open problems that we think about and we try to solve, and some of these take years. So there have been there was a problem which I solved. I was thinking about for 8 years. So then something happened, and then I found a way to solve it. So if you are stuck solving a problem for an hour, then you can imagine in the life of professional mathematician, you can be stuck for 8 years. So it doesn't mean that you don't do anything else for 8 years. You do other things, but you have this thing in the background that you want to solve. And then there are other problems which, there are some problems which I have been thinking about for 15, 16 years now, and I haven't been able to solve them yet. So I'll tell you one of those. So I was thinking very hard, like, is there something I can tell? So I think there is at least one thing I can tell, because the issue is that it's almost like building a language. Like, for example, suppose I want to teach you something in French. Okay, so none of you know French. So or maybe none of you know French. So then I have to start from the beginning, how to, and then you have to. So it's impossible, you see. So that's, it's like the math language is like that. So it's sort of like this French that you have to build up over the years, and so it's sort of impossible to say most math problems to an audience which is not familiar with that. But I will try. I'll try to give you at least one example of a problem that I have been thinking about for the last 15, 16 years. I've not been able to solve. And so maybe you'll see the kind of things that we think about. So there is this. Okay, so let me start with some very simple example. So how can math give you results which are not expected? Okay, so that's one of the other things that's the fun of thinking about math, is that you in the real world you think about something and there is often some intuitive thing. Okay, you feel that this is a solution, but in math, you may not think about something which is you may have some intuition which is completely false. So let me give a very simple example of something which is completely accessible, even for the class 6 students will be accessible, and it's sort of very relevant in the modern world. So here's an example, a very simple example where math gives you an answer which you don't really understand without the math, but it's very simple math. It's just extremely elementary math. So for example, so suppose a very small percentage, so let's say 0.5% of the population has a certain disease. Okay, so it's a sort of a rare disease. 0.5% of 1 in 200 people have a certain disease. Okay, there is a test. There is a diagnostic test for the disease. Okay, so which is 99% accurate. Okay, so that is, if a person has the disease, the result is 99% likely to be positive. And if a person does not have the disease, then the result is 99% likely to be negative. Okay, so suppose that's the setting. So now, suppose someone tests positive. So some random person tests positive. What is the chance that the person has a disease? So how likely is it that the person has the disease? So you see, in this time of the coronavirus, this kind of thing can come up. So there's some disease which is relatively rare in 0.5% of the population. There's this diagnostic test which is 99% accurate in both cases. If you have the disease, it's 99% accurate. With 99% chance, it predicts the correct. It's positive, and if you don't have it, then 99% it turns negative. And suppose someone tests positive, then how confident can you be that the person has a disease, right? So you would intuitively think, oh, it's very likely. It's a 99%, so it's very likely. It's actually not. So actually, you can be about 33% certain that the person has a disease. So let me tell you why. So this is just an example to demonstrate that math can lead to strange results. Which so math is all about logic. Mathematics is just logic, but with symbols. And if you usually if you the amount of logic that you can put into one page of math, if you try to write it in English, it will take 10 pages. So that's why mathematical symbolism is useful. So in this case, however, to make sure that everybody understands, starting from class 6 to class 12. So I'll not go into the symbolism. So this is a problem. Some of you may know this. The older students may know this is the problem Bayesian probability. But I'll just demonstrate with numbers. I'll not even write down any symbols. I'll demonstrate numbers. Why is it that you can only be 33% sure that the person has a disease, even in the scenario? So why? So suppose 1,000 people are tested. So random samples. I'm not going into all those details. So let's say completely random sample. 1,000 people are tested. So 0.5% of 1,000 equals 5. So you can expect 5 people to have the disease. Okay, so roughly around that. Maybe it's 4, maybe it's 6. Anyway, so on average, 5 people will have the disease out of 1,000. Okay. Now, so they're all tested. So all of these 5 people will likely test positive because the test is 99% accurate. So all of these 5 people will test positive. Among the remaining 995 people, so suppose so you have the remaining 995 people, the test will actually falsely diagnose 1% of them as positive. So you see the test has a false positive rate also. It is 1% false positives. So among those 995 people, 1% will test positive. So roughly 10 people out of these 995 will test positive. So what do we get? 5 plus 10 equal to 15 people will test positive. Okay. Of them, only 5 are really with the disease. Okay, so that's why, so 5 out of 15, so that's 1/3. Okay, so that's why, if somebody tests positive, and you can repeat this instead of 1,000 people, you can do it 2,000 people. In general, it's n people. Okay, n going to infinity. You can do all these things. So you will see that this is. It'll not be exactly 1/3. It'll be slightly different from 1/3. I did some approximation here. 995. It'll be 9.95 instead of 10. But roughly, you will see that you can only be 33% sure that if a person tests positive, that the person actually has the disease. And so this is the kind of thing. This is a simple example. This is Bayesian statistics. And if you learning Bayesian statistics in a class, they will do it with symbols and so on. But it boils down to this. Okay, so it's something inherently that you can explain just with some numbers. Okay, so this is a surprise element of math that you can have these surprising scenarios come up which you would never have guessed. Just kind of thought logically, like I think like a logical person. You have to actually do the thing. Okay? Otherwise, you wouldn't come up with this kind of thing. So let me tell you a story about this, a much more complicated story. Okay, than this simple thing. So this was when so the greatest mathematician of all time, as they say, is was Carl Friedrich Gauss. So just as in physics, you have Einstein or Newton. In math, you have Gauss. I think most of you have heard of Gauss. So when Gauss was 19, he was he completed his PhD when he was 19. He had this proof of the fundamental theorem of algebra when he was 19, and so he completed his PhD. Now at that time, you wouldn't get a job. So this was in the early 19th century, I think, sometime around that. You wouldn't get a job even if you complete a PhD. There was no guarantee. Nowadays you get a job if you complete a PhD, even if you prove the fundamental theorem of algebra, you don't get a job. So he didn't get a job. So then he spent a couple of years writing this book called Disquisitiones Arithmeticae, that that's this 800-page book on number theory, which collected the first 400 pages were all number theory that came before Gauss, and then the remaining 400 pages were his own invention. So that's what he did. So this was this revolution in number theory at that time, and in general in math. So he finished it when he was 21, and he still didn't get a job. Okay. So then, what happened was something quite extraordinary, which is so there's this asteroid called Ceres, okay, which is now known as an asteroid, but people thought at that time it was a planet, and there was, so now you see all these, this excitement about exoplanets, which are planets in other galaxies, but not that at that time, there was this excitement about planets in our own solar system, new planets being discovered. So people were, following these this planet Ceres, which was discovered, and they were, it was going to space, and they were keeping track using telescopes, and suddenly it was lost, so they couldn't find it anymore. And everybody was trying to solve that problem. Where is Ceres? Okay. So what Gauss did was he looked at this data. Okay. And he invented a few things. And one of these things is what I'm going to talk about, but I'm almost out of time. So, but anyway, I'll continue. So he had this idea of doing regression. So some of you may know about regression, linear regression in statistics that we do. So he invented least squares regression. And to solve a least squares regression, a high-dimensional least squares regression problem, you have to work with matrices. You have to invert matrices and all that. So things that you learn in school now, inverting matrices. So at that time, none of that existed. So Gauss basically invented this whole field, the linear algebra, the matrices, and how to invert matrices, Gaussian elimination. So it's called Gaussian elimination. So he invented that, and then he realized that this data has this errors in the data. So there were some errors, and these errors had a certain distribution. So this is what's called the Gaussian distribution, the bell-shaped curve. You may have heard of that, the bell-shaped curve. So he proved what's known as a central limit theorem. So that's one of the things that I work in, the central limit theorem. So he proved the central limit theorem. So using this Gaussian distribution and central limit theorem and linear regression and the matrix theory that he developed, he did the regression, and it's available in a Dover publication. He computed by hand up to some 10 places of decimal, something like that. He did that, and then he found this location of Ceres, and they could find it there, and then he got a job at the Astronomical Society in Germany. So this central limit theorem, it's called the Gaussian distribution, comes from that, and you can see it everywhere. So you may have seen this bell-shaped curve. So it looks like this. So what does this mean? It means that what's the histogram of a distribution? So if you have, let's say you have errors in measurement, and then the errors can be 0, -1, 1, and it can take intermediate values also. And then you draw a histogram. So I suppose many of you know what's a histogram. So it represents how many errors that you see falling in a certain region. And the error distribution is always something like this in this Gaussian distribution. So which is formally the function. So this is for the more senior students. So something like this: y equals e to the minus x squared to this kind of curve that you see. And so there are many things that are supposed to follow this central limit theorem, this errors in measurements, this same distribution, the Gaussian distribution, which we cannot prove that they occur. So let me close with this example that I have been trying for the last 15 years, as I said, and this whole class of examples is just one example. So this is called what's called the traveling salesman problem. Okay. So let's say a very simple scenario. You have a square box and you have some cities here. So this is some randomly distributed cities in a country. So it's a very simplistic scenario where the country is just a square and you have the cities in this country which are randomly distributed. And the traveling salesman task is to find the shortest path through all these cities. Okay, so maybe you go like this. Okay, so who knows what the shortest path is? So actually, it's an open problem to show that it's one of the big open problems to show that you cannot do that in any reasonable time. So it's one of these NP-hard problems, or they call the PNP problem. So there is no good algorithm for doing that. But anyway, the task is, suppose you want to find the shortest path through all the cities. So there can be many different ways for going through all the cities, and there will be shortest path. And suppose you can actually find the shortest path and look at its length. So the conjecture is that this length, each time you have this random scattering of points and you compute the length of the shortest path, it will have a certain slightly different value. And if you draw the histogram of these values that you get by repeating this experiment many times, you would again see this Gaussian curve. Okay, and that is completely open. So we have no idea how to prove this. I mean, well, we have some idea, but we don't know how to complete the argument. So this is an example of a problem. So it's just, as you can see, it's very hard for me to say this in a way that's intelligible to especially to the younger students. But I made a valiant effort, I think. But okay, so anyway, so this is one example. But at least I wanted to say something which everybody will understand. So, but I shouldn't overshoot. So I've been speaking for 25 minutes. So let me stop here, and I look forward to the questions. So if you guys have questions, that'll be great. I'll be very happy to talk about more things in the questions. So thank you.
I think that just left us wanting more. Srina ma'am will take us through the questions. Srina ma'am, are you ready?
Absolutely. Thank you so much, sir. That was really wonderful. And what I take it from here is that a lot of patience is required for problem solving, and we should never give up. So that was really wonderful, sir.
Yeah.
And as we come towards the end of the session, the floor is now open for questions. So all those people who are ready with the questions, I would request them to kindly raise your hands, and we'll call out your name. So please unmute, and it would be better if you could switch on your cameras as well, and you can ask the question. So yes, we have Medha here. Medha, you can unmute and ask your question.
Yes, ma'am. Thank you. So, namaste, sir. I will be very honest. I don't like maths. But I still have maths. I'm in 11th and I have maths. So, I have two questions. The first is, how can I make maths enjoyable for myself? And the second question is, so I have a good grip on the theory, but I'm not so good with the numbers. So how can I improve my grip on numbers?
So you see, interest in something is dependent on how much success you get in it. Okay, so if you do problems and you get better at it, and you can solve more and more problems, and you can solve on your own, and you see that you are able to do it on your own, and your interest is going to increase. So interest varies by that. So if you fail, then your interest is going to go down. Okay. So the thing to remember, is to be always optimistic that, I'm not able to do this now, but I'll be able to do this if I practice hard, 3 weeks from now. Okay. So then I really try, and then maybe in 3 weeks you will see that you are solving several questions that you were not able to solve before, and each time you solve something, your interest is going to increase. Okay, and it's going to get better and better. So this interest thing is not permanent. It's just the function that you are not able to do something right now, which is kind of killing your interest. And so optimism is the key, that you have to believe that if I try for 3 weeks, I'll be able to do this. Okay. Sure.
Thank you, sir. So we've come to the end of the questions, and now I would request Annapurna ma'am to give the vote of thanks.
What do I say, Professor Chatterjee? This has been such a delightful. Thank you, Trina ma'am, first of all, for moderating it so well. And Professor
Definitely.
Chatterjee, it has been an absolute pleasure for us to have you this morning. And while you shared that it's difficult to bring to a range of children from from class 6 to class 12 the complexities of math and all that is there about math to say, you have given us a lot of things to think about. So I loved your expression of how you need to persist even when there is a problem, and we wish you the very best with the traveling salesman problem.
Problem.
And
Yes.
yes, and I'm sure today we have here in the audience about 128 attendees, uh, children. Some of them definitely will take on math as a career, and some of them also might take up research and statistics and probability, maybe because of this one interaction with you. And that's the aim, to
Yeah.
give them the exposure and to get them to start thinking. So thank you so much for taking out your time. The time, it's evening now for you. So to squeeze out time for this session and to do it, you've been brilliant, sir. You may have had you may have some reservations about addressing children, and this could be your first time after grade 7, but you've really been brilliant. Don't you agree, Sonali ma'am?
Absolutely, sir, and very beautifully shared, sir. My takeaway is again, children, I would like to reiterate, while things seem tough sometimes, but that's not going to be permanent. You are going to get over it, right? And I loved the way Professor Chatterjee explained the problem with the disease. So relevant today
Yes.
because it is math is about real life application, right? So I connected so well, and I was thinking, so why are we so scared of the virus here? If you are looking in terms of the world population, the number seemed so small. Even if you took 1,000, imagine the whole world population. And now I understand why people, a lot of people around me are saying, well, it really doesn't matter. So while we are hoping for a cure and a vaccine to come out and world to get back to normal, thank you, sir, for also explaining so in such easy terms that it's not such a big deal. Yes, it is there, but then again, going back to what you said, it's not going to be permanent. We are going to get over it and sit back and look and say, see, that's what the maths was all about.